The title of my presentation topic is Materials Designed for Energy and Environmental Application. I have little bit changed my title because I want to show some of my previous results. Before going to my topic, let me discuss about solar energy. According to the statistics that is reported by International Energy Agency, the world energy consumption in a year is before going to my topic, let me discuss regarding solar energy. The world energy consumption in a year is equivalent to 16 terawatt, but the solar energy that is really absorbed on the surface of the earth is around 89 picowatts. So this result suggested that we have lost 5,000 times of solar energy in each year. So if we want to utilize solar energy, this is the one of the efficient way, that is the sun is abundantly available and the water is the abundant source in the universe. So utilizing a particulate photocatalyst, we can efficiently produce hydrogen gas. This is the basic principle behind photocatalytic water splitting. When light of sufficient energy is fall on a semiconductor nanoparticle, there is excitation of electron from the valence band to the conduction band, and the valence band side it oxidizes water to O2 gas, and the conduction band the free electron reduces proton to H2 gas. But the most important factor is here is recombination, because the electron that is in the excited state, it is quite unstable and it tend to recombine with the hole, and this recombination process always decreases the efficiency of a photocatalyst. So in order to develop efficient photocatalyst, we must have to consider these points like absorption efficiency, charge separation efficiency, charge transfer efficiency, and charge collection or carrier efficiency, because the mone efficiency loss is mostly due to the electron hole recombination. How to improve the charge transfer, the light absorption efficiency? In this regard, I have developed a material that is a nitrogen doped gallium zinc mesoxide. The gallium zinc mesoxide is originally active under UV light, but when I dope with nitrogen, the optical absorption is clearly shifted towards the visible region. This paper was published in Journal of Material Chemistry, and I have also successful in modifying the surface structure of the material. I have got various morphology, and this material showed highest activity, very good activity towards hydrogen evolution. So then the next question is how to increase the charge separation efficiency. So modifying a heterojunction, giving importance to heterojunction photocatalyst, we can improve the charge separation efficiency. In this regard, I have developed this material, that is I have modified zinc oxide with indium oxide, and this material is reported in Journal of Material Chemistry. And this material also gives very good hydrogen evolution under visual light irradiation. This is also another material, and this paper has been published in Inorganic Chemistry. And then how to improve the charge transfer efficiency? So designing a 1D or low D material, we can improve the charge transfer efficiency, because in a 1D material whole transport with a short diffusion distance, the light absorption with a long attenuation length, and the vectorial electron flow through axial direction. So in this regard, I have developed this material, and this material is published in Dalton Transaction in the year 2012. Then how to improve the charge collection or the charge collection or the reaction efficiency? So in this regard, we can deposit some co-catalyst, or also we can utilize some charge transporter like graphene oxide. In this regard, this paper has been published in various good impact journals. So what is graphite carbon nitride? Whatever material I have discussed, all are metallic material. Then that I have produced during my PhD study. But now I am focusing on the graphite carbon nitride. It is a high surface area material. It can split also water molecule, and it is a different carbon source. But the most important thing is it is a non-metallic photocatalyst. So in this regard, I have developed this material, the highly active graphite carbon nitride. Generally, it is prepared by utilizing a urea source or melamine source. So, but in this paper, I have just mixed the unimolar ratio of urea and melamine, and I have successfully modified the surface structure, the internal structure of the graphite carbon nitride, where I have mixed the melamine and urea in unimolar ratio. The two-dimensional layer of graphite carbon nitride is well separated, and it shows very high activity than the material prepared from only urea and the melamine source. And this is the work that I have submitted to Indian Science Congress. This is one-step synthesis of graphite carbon nitride powder photocatalyst and thin film. Actually, most of the work that I have reported by taking the graphite carbonated regarding powder photocatalysis, but it is very difficult to synthesize the thin film because its conductivity is very low. So here I have adapted some a unique technique where I can synthesize in one step powder photocatalysis as well as the thin film. So I have taken melamine, that is the carbon that source containing the carbon and nitrogen in a crucible, and I put a FTO plate. The FTO surface as it is the conductive surface, so it is faced towards the sample. When I heated it for 550 degrees centigrade for 2 hours, I can successfully synthesize thin film only a single step. So I have characterized this method by XRD, and the XRD technique showed that this material is successfully prepared by taking the powder and as well as also the thin film. And this 002 peak is due to the interlayer distance in the graphite carbonate thin film, and this the 100 plane is due to the hole to hole distance in the trigen unit plane of the graphite carbonated. This is the EV visual DRS study of the powder as well as thin film. Both the material could able to absorb the visible light irradiation, and this is the FTIR spectra. In the FTIR spectra, and the all kind of bonding like the bonding due to trigen units, and the carbon nitrogen single bond and the carbon nitrogen double bond, all the bonding are confirmed from the FTIR spectra. And but in case of powder, I found that there is a broad absorption spectra at around 3000 to 3500. It is mostly due to the surface absorbed water molecule. But in case of thin film, although this peak is there, but it is very less. In case of same, when I studied the surface morphology of the material, I found that the material that is obtained in the powder form, it is quite agglomerated, but the material that I obtained in the thin film, it is clearly to 2D like structure. So if I consider how can I improve the surface structure, it is one of the best material where we can easily modify the surface structure of the material. In the XPS study, I found that both in case of thin film, I found that this material well satisfies all the condition on all the electronic environment. The carbon bonding, the carbon nitrogen bonding, and the nitrogen carbon bonding, all are confirmed from the XPS spectra. And from the photocurrent study, I found that the material I prepared in the powder form, it could able to generate 0.02 microampere current. But when the film I obtained in a single step method, it gives around 25 times higher photocurrent than that of than the material obtained in the powder form. And this is the unique study of my material. Until to date, whatever literature reported, this is the highest ever photocurrent obtained by taking the G-thin film that I prepared in a single step. So, but although I have prepared in a single step, but further surface modification required to improve the photoelectrochemical properties of film, because for fish application this much current is not sufficient. When I tested the powder catalyst towards particular activity, it retains its own activity. It could able to generate 17 micron hydrogen gas in 3 hours of light radiation, and also could able to degrade 100% of 100 ppm rhodium solution. So putting it all together, in order to design efficient photocatalyst, we have to look towards heterojunction, towards all the nature of a photocatalyst. We have to look go to heterojunction. Also, we have to put some conductive scaffold like graphene, also utilizing co-catalyst doping. So, to develop a efficient photocatalyst for industrialization of the process, we have to look all the points. So now we are at the 5% efficiency. So, yes, creative material design is a new vehicle to the goals, and it is my final conclusion. These are some of my publications, and within this year I have published 30 articles with the citation factor 981, FOH index 16, and ITN is 26. And these are ongoing projects. Now I have one project as principal investigator, and three projects are co-principal investigator. Finally, I thanks to my Professor Poidas group, he is my supervisor. Under him I have done much of the work, and thanks a lot for your nice hearing.